today is Steffen Lempp, telling us about minimal coverage in the Weihrauch degrees.
Thanks, Dennis. Thanks also especially to the organizers for inviting me to speak here. So it's great to see this regional seminar continue for I think 15 years now.
Yeah, this is number 32. So.
Number 32, 16 years, I guess, plus pandemic, whatever. Anyways, that's a long time. I like it. So I want to talk about work that happened last spring when Arno Pauli was visiting Madison, and Joe, Arno, Maria, Manlio, our former postdoc, and I were able to come up with a particular result which seemed technical at first, but then actually turned out later to give us a whole bunch of corollaries that were really nice. But since this is not a computability theory only crowd, I figured I should probably give a little bit of motivation for why people would even care about bioreducibility. So let me start with a very general outlook on what's going on. So let me first say what I'm going to call a mathematical problem. So a mathematical problem, especially since it's going to be a pi 1,2 statement, it's a statement of the form for any set x. If the set x satisfies some property phi, then there's a set y such that x and y together satisfy some formula psi. Phi and psi are formulas in called second order arithmetic, which is actually just a two-sorted language of arithmetic. So plus times less than 0, 1 and an element. And phi and psi, they're allowed to use set variables, but they're not allowed to use set quantifiers. So they only use number quantifiers, so it means they're arithmetical formulas, if you want.
Steffen, can I just get you to share the screen?
I'm sorry?
You share the screen. Zoom talk.
Oh,
You connect to the Zoom meeting.
Oh, sorry. Yes. No.
so somebody, I'm glad somebody noticed this.
Yes, thank you.
On Zoom. And if you were recording it,
Are we recording?
we are. I mean, we don't have to.
No.
I don't care either way. You have more permission
I forget about that.
record or not record?
There's one person on Zoom. No.
Right.
Turn, no.
Right. No, it's fine. I'm muted. Share this game.
We're gonna get rid of this on top of. I think we just throw it away at the bottom.
And you should also stop the video.
No. What?
Stop video. This computer's camera is also on right now.
You put this computer.
Okay.
All right. Maybe I should start again. So. No, that's okay. Oh, you know what? Now the things don't work anymore. The advance. The buttons. Sorry. Maybe I need the thing here.
Yeah.
Wait, which worked?
Oh, it's the arrows.
Huh?
The arrows.
Yeah.
Yeah.
Oh, okay. Didn't work. Okay. All right. So let me start very briefly. So it's joint work with Arno Pauli and group with Madison, Joe, Maria, and Manlio. I start by defining a mathematical problem, which is a pi 1,2 problem, a pi 1,2 statement in the language of second order arithmetic, which is really a two-sorted language for first order. For first order language, where plus times less than 0, 1 element relation, and phi psi are simply arithmetical formulas, that meaning they're only allowed number quantifiers, no set quantifiers, but we're allowing set parameters in the whole thing. So in this context, capital X is typically called an instance of the problem, and capital Y is called solution of the problem. This sounds a little abstract. So let me just give you a couple of standard examples to just tell you how you should think about this. So weak-Koenig's lemma is a statement: every infinite binary tree has an infinite path. Okay, so you can formalize this in this language as saying, well, X codes some infinite binary tree in arithmetic, and phi says that X is an infinite binary tree, quote unquote, under some coding. And then Y is an infinite path to X is coded by the formula psi. This can all be done using only number quantifiers. So therefore, weak-Koenig's lemma can be stated as a mathematical problem in the sense of line 2 of this slide. Similarly, Ramsey's theorem for pairs in two colors can be stated this way, because you can say in a formula, X is a two coloring of unordered pairs of numbers. This is what little phi says. Capital Y is an infinite homogeneous set, and this can be said by some formula psi xy. So that's sort of the setup. And now I want to study this from various angles, and I'm going to use 3 angles. I'm going to concentrate on the last one, but I want to show you that this is something that's been studied in many different ways in logic. So there's a proof theoretic angle that many of you will be probably familiar with. There's a model theoretic angle. I mentioned this just because this is joint model theory seminars. I had to mention the word model theory once. I will do it one more time, and that's it. Sorry. And then there's a computability theoretic angle. So the proof theoretic angle is the reverse math angle. So what you do is you work over some weak base theory, typically something that sort of basically allows you to do computable mathematics. And RCA naught is sort of the standard system. So it's PA minus, which is the axioms for a discretely ordered semi-ring, commutative. And then you also have sigma 0, 1 induction. So just sigma, so induction over sigma 0, 1 formulas. And you have delta 0, 1 comprehension, meaning if a set is definable over the model with a sigma 0, 1 and a pi 0, 1 formula, then it actually exists in the model. Because technically, we have number variables, and we have number objects, we have set objects, but the set objects don't have to necessarily be the complete power set of the number objects. So therefore, we have to worry about that. And then reverse mathematics is a way to measure the proof theoretic strength of mathematical problems into the usual proof calculus. Take your favorite proof calculus from a first semester logic course, and that's precisely what you get. For example, one can now show, and these are very, very hard theorems. I don't want to, but I'm going to push this on the rug a little because this is not going to be my focus. But just for an example, you can show that weak-Koenig's lemma and Ramsey's theorem for pairs in two colors are actually independent over RCA naught. Neither implies the other over the weak base theory. But, for example, Ramsey's theorem for pairs in two colors and Ramsey's theorem for pairs with 3 colors, they are equivalent. You can show one from the other. But these Ramsey's theorem for pairs is strictly weaker than Ramsey's theorem for triples, for example, for 2 colors. Just to give some concrete examples of sort of what kinds of combinatorics is going on there. So some of this is called the zoo of reverse mathematics, and combinatorics is particularly suitable for generating a lot of inequivalent proof theory principles which correspond to mathematical problems. So on the one hand, this approach seems less restrictive because we can use assumptions repeatedly, right? The reason that Ramsey's theorem for pairs in 2 colors and 3 colors is equivalent is because I could just apply Ramsey's theorem for pairs with 2 colors twice, and then I get 3 colors. On the other hand, from a model theory point of view, I've said model theory twice already. So from a semantic point of view, this is actually something which is hard because I have to work not just with the usual model arithmetic that we're all familiar with from grade school, but there's these non-standard models, and they may not satisfy full induction, especially not full first order induction. So therefore, things are a little weird. For example, the infinite pitch null principle may not hold in all models, so it does not follow from RCA NOS. Infinite pitch null principle is just a principle which says that if I have a function from the universe into a finite set, then the pre-image of one element in the range is infinite. Okay, that does not follow from RCA naught. It requires delta 02 induction, therefore it doesn't follow from sigma 01 induction. So that's the first angle. The next angle is a somewhat model theoretic one, in a very weak sense. My apologies to the actual model theorists. So instead of considering all models of theory, you can actually look just at the models with the standard first order part. So these are models where the first order part, the number sort is true omega, the actual natural numbers. And then you have a second order part, which is probably some proper subset of the power set of omega. Oftentimes this second order part is thought of countable, actually suffices, but it makes things a little easier to think which is just countable. And so what happens then? Well, now we can work with not a syntactic but a semantic implication. So problem P is reducible to problem Q if every model of Q is also a model of P. Right? So this is another way to think about comparing the strength of problems. This approach has not been explored that much. It's sometimes called omega model reducibility, and then denoted as Q double turnstile sub omega P. So because Q is greater than or equal P in some sense, right? So it avoids these quote pesky problems with induction. On the other hand, it's nice because infinite pitch null principle just holds outright, because we're now in true omega, so of course pitch null principle holds for all models of RCA naught, because now we're looking at models of RCA naught where the standard part, where the first order part is just true omega. Okay, so that's the second angle. And then for the computability theory angle, I want to actually look at two different ways. There is a somewhat less restrictive approach, which is called computable reducibility. So principle P is computable reducible principle Q if the following holds. I take an instance for P, and I compute from it somehow some instance for Q, called it X hat. So here's X, instance for P. I compute an instance X hat. Now from this instance X hat, Q, which I assume is a black box, gives me some solution Y hat, which is this is solution to the problem for Q. And now from Y hat and the original X, I can compute this solution X to the principle P. Okay. So what this does is it says, okay, so I can actually solve P using Q, but I'm doing this in a somewhat very uniform, well, in a computable way, right? I generate an instance of Q. Q gives me a solution, and then from that solution, I compute a solution to P again. So it's more restrictive because I can use assumptions only once, but I can argue computably theoretically, which means, for example, I don't have to be uniform. We'll see in a second how that makes a difference. By the way, I should mention that if Y can compute from Y hat only without using the original input X, that is sometimes called strongly computably reducible and has a special notation. Just for an example, Ramsey's theorem for pairs with 3 colors does not computably reduce to Ramsey's theorem for pairs with 2 colors, because if I want a homogeneous set for 3 coloring, I need to basically apply Ramsden for two colorings twice. I can't just do it once, and that's the problem. So this is why this is a more restrictive approach than the previous two approaches. And then an even more restrictive approach is Weihrauch reducibility. So let me state that carefully, and then I'll mention some more about what Weihrauch reducibility actually does about this. So the difference between computable reducibility and Weihrauch reducibility is that we require a lot of more uniformity. So P is Weihrauch reducible to Q if there are actual Turing functionals, phi and psi, which sometimes called the forward functional and the backward functional. So the forward functional phi from an instance of P, x, call it x, it computes some instance x hat of for Q. That's by phi, and then magically Q gives me some solution y hat, and now from y hat and x I can compute via psi uniformly this x. This is a uniform version of the previous slide, and this is the most restrictive approach of all the ones I mentioned here, because we're allowed to query Q only once. But also we're only allowed to do it uniformly. It has to be a uniform algorithm which produces x hat from x and which produces y from y hat and x. And again, just like before, there's a strong version where if you can compute y hat from x hat only, we call it strong Weihrauch reducibility. I'm not going to worry about this too much, but just want to mention that this is a variant that has been considered. Now we have things that are kind of weird, so I didn't define this carefully, but there's this principle called DNR2 and 3 and whatever. So DNR2, diagonal non-recursive for 0, 1 value function versus diagonally non-recursive for 0, 1, 2 value. These are computably under computable reducibility the same, but DNR2 does not Weihrauch reduce to DNR3. Okay, so you get something that the uniformity really makes a difference. I mean, this uniformity, somehow makes it harder to get these reductions. Okay, so this is kind of the end of my introduction to why Weihrauch reducibility, and what I want to now talk about is the degree structure. So let me turn around a little bit and say, okay, a lot of research in Weihrauch reducibility came from applications to actual mathematics. I mean, you want to represent actual problems from normal mathematics like combinatorics in particular, but can be anything like analysis, topology, algebra, whatever. And of course, you don't just look at bare space, but we're going to actually just look at bare space, and we are instead of looking at arbitrary space, we're going to just look at bare space. And normally, when you do Weihrauch reducibility, you represent objects in your spaces by names in bare space. And there's a lot of representation theory going on, which I don't want to get into. I'm going to simply restrict to bare space only. I'm going to consider only problems in bare space. And now I want to talk about Weihrauch degrees as a degree structure. So I'm going to change rotation a little bit. Okay, so rather than talking about mathematical problem P and so on, I'm going to think about partial multi-valued functions, which is basically the same thing. It's now just restricted to bare space. So think of the problem with instance X and solution Y. So what's really going on is that I have some X for which the formula phi holds and some for which it doesn't hold. So the domain of the function little f, which is now representing my mathematical problem, is going to be just some subset of bare space, namely the set of all those x for which phi x holds. And then it's a multi-valued function in the sense that there is not a unique solution for x. I mean, for example, if you think of Ramsden for pairs, of course, if you have 1, 2 coloring, there can be many, many different, in fact, there will be many different homogeneous, infinite homogeneous subsets. So therefore, for every x, there can be many solutions y. And the set of all these solutions y, which satisfies form psi xy, that's going to be the output of my function f. So that's what I mean by multi-valued function here. And now I can talk about, I can define the set of partial multi-valued functions. I'll call it PF. And the degree structure I'm going to talk about is the quotient of the partial multi-valued functions modulo Weihrauch equivalence, which of course is just saying two things are Weihrauch equivalent if and only if they're interreducible under Weihrauch reducibility with the induced partial order. So remember, Weihrauch reducibility, of course, is a pre-partial ordering on Baire space on PF in this sense. So if I take the quotient, I get a partial ordering, and this partial ordering is going to be some degree structure which I now want to study. So let me start with some really basic facts. In fact, it's actually amazing that about this structure, there's actually not a lot known from a set theoretic point of view. So Manlio got me interested in this when he arrived a year and a half ago in Madison. So first of all, W is a partial order. It has least element 0. 0 just corresponds to the empty function, right? I mean, this is the easiest problem, obviously. Under a very mild version of the axiom of choice, you can show that W has no gradius or even the maximal element. Okay? So it's unbounded above. Okay? So it's an order in which it's 0 at the bottom and then it goes like this. Second, W is big. It's size 2 to the continuum. Okay? So it's much bigger, for example, than Turing degrees that you might be used to. Furthermore, every individual Weihrauch degrees, except for 0, of course, has also size 2 to c. Okay, so these are very large degrees. It's because basically when you have partial functions, you can think of like restricting the partial functions to subdomains, and you get a lot of different representatives. Every non-trivial lower coordinate W has size 2 to c. So this is very, very different from Turing degrees where we have locally countable. Every non-trivial maximal anti-chain W must be uncountable. But there is a maximal anti-chain of size 2 to c, but nothing more is known. We don't know whether there are maximal anti-chains of size less than 2 to c, except of course for the trivial anti-chain single to 0. That's not interesting. The next question one might ask from a set sort of degree theory point of view, well, what about ascending chains? In particular, I want to look at well-ordered ascending chains. I want to basically enumerate things upward, right? Just to label them by ordinals. So every well-ordered ascending chain in W, if it has countable cofinality, it must have an upper bound, right? Just simply take the uniform join of what you got so far, so you get an upper bound. However, for every cardinal kappa less than the continuum, as if it has uncountable cofinality, I can build an ascending chain in W of order type kappa, which has no upper bound. This is not known for kappa size bigger than the continuum, but less than 2 to c. Okay, so it could be that there may be ascending chains, without upper bound in those sizes, but at least for size up to continuum, we know. By the way, this is this work that I'm mentioning here is work that was that's Manlio Valenti and Alberto Marcone mostly. They thought about these kinds of questions. That's how got me interested in the abstract degree structure of this thing. There's another thing I should mention. So apart from just the partial ordering, there are also quite a few natural operations on the partial multi-valued function that have been defined. Some of the degree theoretic, which means I can actually, they actually work well with degrees, that they're independent of the degree that I'm representing. Some of them don't. So therefore, I just want to mention a couple which are degree theoretic, because they're meet and join, which make them into a distributive lattice. So I can define for partial multi-valued function f and g, I can define the join by simply saying f join g is a function which can basically compute both f and g. You just give the input which one do you want to compute, and then some input x, and then it computes either f of x or g of x. And then the other, the meat is you take f and g, and you give it two inputs x and y, and then f meet g will compute either f of x or g of y for you. It tells you which one, but doesn't compute both. Okay, so that is the operation of meet. And that gives you distributive lattice, as one can check. You know, these are checks that have been done. I don't want to go into details. So then for a classical computability theorist like me, right, who comes from studying Turing degrees and so on, the next question, sort of natural question, is like, well, what are first order theory of W under partial ordering? Is it decidable? If it's undecidable, what's the complexity of the theory? And so on. Well, it turns out that there's one degree which is special, and it's kind of a surprising thing because you wouldn't expect the identity function to really be an interesting function, but actually in the Weihrauch degrees it is. So the degree 1, which is just the degree of the identity function, which is just so this is the single valued function which maps every element x in Baire space to itself. This plays a special role in the Weihrauch degrees, and I now want to say a few things about it. So first, I need to take a little detour into another degree structure, which is also lattice. It's Medvedev degrees, and we'll see the connection why I need to take this detour. So Medvedev degrees were studied by Russian mathematician Medvedev, who was interested in intuitionist logic, and he defined this Medvedev reducibility to get results in intuitionist logic, but this actual independent interest has been studied in a lot of other contexts. So the basic notion for Medvedev degrees is the notion of a mass problem. So mass problem is just a subset of Baire space. And then the mass problem A is Medvedev reducible to mass problem B if there is a Turing functional which maps every element of B to some element in A. So in particular, for every x in B, phi of x is a total function. It is again an element of Baire space. So for any x in B, you get something in A, and because phi of x actually converges, it's a total function, and it's something in A. Right, so that's that compares mass problems. So now again, just like with Weihrauch reducibility, of course, I can study the space of all mass problems, which is the powers of Baire space, modulo Medvedev equivalence. That's again a degree structure, and this is the degree structure of the Medvedev degrees, which is again a distributive lattice. I'm not going to tell you what the lattice structure is. It's kind of similar. The definition is kind of similar to what we've already done. And now there's a connection now between Medvedev degrees and Weihrauch degrees, which is given by this function d sub a. So given a mass problem A, some subset of Baire space, we can define the function d sub a to be the partial function which maps every x in A to just a trivial string all 0. And it doesn't define x. If x is not in A, it's just partial. It just doesn't do anything. Okay. Of course, notice that from a Weihrauch point of reducibility kind of view, d sub a is the same as just the identity function restricted to the mass problem A. Because I mean, sending x to 0 or all zeros or sending x to x is the same thing, as long as the domain is the same. Okay, so this is this notion. Now, this dA was used by Higuchi and Kihara to define an embedding of the Medvedev degrees into the Weihrauch degrees, but it's actually the Medvedev degrees upside down, so under the reverse ordering. So this is kind of a weird thing, but if you think about it, it makes sense. So Higuchi and Kihara defined this operation from A to d sub a, and if you look at the degree theoretic side, it maps a Medvedev degree to a Weihrauch degree, and it preserves the ordering if you reverse the ordering on the Muchnik degrees. On the Medvedev degrees. I should mention, by the way, that a couple of years before Higuchi and Kihara came up with this definition, Radka and Gerardi came up with a different embedding, which is not the one I'm going to be using. But I mean, the one I'm going to use is the one by Higuchi and Kihara, because that's the one that I'm going to be using in what follows. So the special thing about the embedding found by Higuchi and Kihara is that it's onto the cone of the Weihrauch degrees below the degree 1, below this degree of the identity function. So therefore, what we have is we have an isomorphism between the Medvedev degrees under reverse ordering and the Weihrauch degrees below this degree 1. And also, it's not hard to see that the Weihrauch degrees below 1 correspond precisely to all the Weihrauch degrees of restrictions of the identity function to any mass problem whatsoever. Okay, so this is a special class of Weihrauch degrees. So the question is then, well, wouldn't it be nice if this degree 1, which is just some degree that's sitting somewhere there, right? This were definable. Remember, every non-trivial Weihrauch degree has, bounds to the C many Weihrauch degrees. So therefore, it's not so clear why it should be definable. But this was the question that Arno came to us with when he visited last spring. It's actually a question that he had posed 4 years ago. Is the special degree 1 definable in just the partial ordering of the Weihrauch degrees? And it turns out that actually it is definable in not only one, but 2 different ways. The degree 1 in the Weihrauch degrees is definable, first of all, as the greatest degree, which is a strong minimal cover in W. So a strong minimal cover is a degree X such that there is some degree Y below it, and every degree strictly less than X is already less or equal Y. It's not just that the interval between X and Y is empty, but actually the difference of the 2 cones is like the difference between the cone below X and the different cone below Y is just the single degree X on top. Okay, so that's the first definition. And then the other definition we came up with as a side product is 1 is also the least degree, such that the cone above that degree is densely ordered. It's kind of surprising that you get these 2 quite different definitions, but so basically below ID things are very bad. There's strong minimal covers, all kinds of stuff, and above it's nice because it's densely ordered, right? Of course, it's still, I mean, this is we're talking a structure count of size 2 to C, so it's not that nice. It's a it's a partial order, but anyway, it's a stark difference. Now, using this definability of the degree 1, we can now apply a theorem of Louis Pye, Nice, and Sorby, also independently by Schaefer 2 years later in his thesis, published 2 years later as part of his thesis, that the first order theory of the Medvedev degrees is complicated as third order arithmetic, which makes sense because remember, Medvedev degrees also have size 2 to C. So you would expect third order arithmetic to crop up there. So that's what they showed. And then since Medvedev degrees are isomorphic to the Weihrauch degrees below 1, and since 1 is definable, we get as a corollary that the first order theory of the Weihrauch degrees is also as complicated as third order arithmetic. But of course, this also holds true for the Weihrauch degrees below 1, but that's not the interesting part. The interesting part is that it's actually, since 1 is definable, we get the first order theory of all the Weihrauch degrees is as complicated as third order arithmetic. Okay, so now I want to explain a little bit about how one would prove those 2 statements, those 2 different ways of defining 1 in the Weihrauch degrees in the remaining 16 minutes. So let me just sketch a little bit about what's going into the proof. I'll just sketch some components. By the way, I should mention this paper is already on my webpage and the webpage of my co-author, so you can download. It's only 8 pages, so it's pretty short, so you can just read it, you know, if you get bored one night. Anyways, so the first component of the proof is the following. If you have an element X of Baire space, you can define X plus, which is the set of all strings starting with the number E followed by an infinite string Y, such that phi Y computes X, but Y is not below X in this Turing sense. So what does that mean? That means basically that X plus is a set of all strings Y which are Turing above X, but strictly so. But it actually has more information, because not only does it tell you that it's Turing above, not only do we know that Y is Turing above X, we also know what the index of the computation is that computes X from Y, right? This is what's coded, this is what X plus is. And then there's an old theorem of Dement from almost 50 years ago now, which says that in the last of Medvedev degrees, I can define the notion of minimal cover in using this definition. So a math problem B is a minimal cover of a math problem A if and only if there's an element in X in A, such that A is B meet singleton X, and B meet singleton X plus is Medvedev equivalent to B. This was this result by Dement, who, by the way, also goes by the name Skvortsova, which is something that even Math Siner didn't know about until I told him a few months ago. But anyways, she got married and changed, you know, her name changed. Anyway, Dement also showed in the same paper that the strong minimal covers can also be defined in the Medvedev degrees. Namely, the strong minimal covers are precisely of the form Medvedev degree of singleton X, comma Medvedev degree of X plus, where X ranges over all possible elements of Baire space. So that's what Dement proved almost 50 years ago. So in particular, the Medvedev degree of being the Medvedev degree of singleton, which is something called a degree of solvability, which has something to do with how Turing degrees can be embedded into Medvedev degrees. This is a definable property in M, because I can say it in this I can use the second bullet here to define singletons. I mean, being degree of singleton just means that I have a strong minimal cover. And the corollary of this is that the Weihrauch degree 1 is a strong minimal cover of the Weihrauch degree of the identity function restricted to all non-recursive sets. So non-recursive sets, of course, is just a Medvedev degree of 0 to the omega plus, or think of it another way, it's just the math problem of all non-computable infinite sequences in Baire space. So that gives us one thing. Now, from Dement's definition of minimal cover and strong minimal cover, we were able to prove equivalent definitions of minimal cover and strong minimal cover in the Weihrauch degrees. So the Weihrauch degrees, the degree of G is a minimal cover of degree F, if and only if I can write G as F join ID restricted to a singleton for some singleton little x, such that that singleton little x is not Medvedev above the domain of F, but the domain of F is Medvedev reducible to X plus. This is a very special property here. And then for strong minimal cover, this is just basically a corollary of the first bullet. It's a special case. Strong minimal cover of so G is a strong minimal cover of F, if and only if there's a singleton such that G is ID restricted to a singleton, and f is ID restricted to to x plus. Okay, so this is the definition we get. So in particular, we have that degree of ID is the greatest, strongest minimal cover in the Weihrauch degrees, because just look at definition here. And every Weihrauch degree also interesting is that every Weihrauch degree has at most one strong minimal cover, which is not something that's obvious, right? So we get that. Now, the critical lemma, which is that the heart of this whole thing, is the following. And I don't want to go through the proof. I mean, the proof is like is somewhat involved because you have to build all this back and forth functional stuff. It gets a little tricky. But the critical lemma is the following. Then I mean that if G is a minimal cover of F, then there is a function H with domain of size 1, such that G is F join H. And if I have a strong minimal cover, then actually I have that the top degree G in particular has to be represented by a function with a degree at most of size with a domain of size 1. Okay, so this is a step along the way of proving the theorem at the top of the page. And just quickly what's going on here. So let me just to show you, I want to show it, at least give you a hint of how the first bullet might be shown. What you have to do is the following. So remember, what we want to show is G is a minimal cover of F, then there's H with domain of size 1, such that F is G is F join H. How do we do it? Well, we construct this scrambling function psi, which is a function from a partial function from bare space into natural numbers. And psi is a countable union of finite functions. And then we define this function capital G sub psi of x comma psi of x, and the output is just little g of x. So it's not hard to see that G psi is Weihrauch reducible to little g for any psi whatsoever. Because I mean, what is if you want to compute G sub psi, what do? You just ignore psi and just output little g of x. Okay, so therefore that's trivial. The thing is, you want to show that the other direction doesn't have to hold, because x doesn't need to know whether psi of x is defined or not. That's the trick, right? It's all about the domain of psi. What is in the domain of psi? So we try to ensure that f is strictly below f join g psi, which is strictly below g. If we're able to show that, and of course, then we have contradict the fact that G is a minimal cover of F, so therefore we better not be able to do this. So at odd stages, we try to ensure that G psi cannot be Weihrauch reduced to F. So via the next pair of functionals phi and psi, phi e and phi I, say some enumeration of all possible back and forth reductions. And at even stages, we try to ensure that little g cannot be reduced to F join G psi. Now, if we're able to show this for every possible pair E and I at even odd stages, then we have a failure of G being a minimal cover of F. Therefore, at some point, this has to start failing. At some finite stage, I'm going to be stuck. I won't be able to extend my function psi anymore. Remember, psi is just a finite function in the finite stage, just some function psi is. But that gives me that G is now Weihrauch equivalent to F join G sub psi s for some finite function G psi s. But that is G psi s. That's just a finite function, which means that it is the join of some functions h sub I, where each hi has domain of size 1. But now, since G is a minimal cover of F, I know that G is actually Weihrauch equivalent to F join some single hj, right? Because G, of course, the degree of G is joint irreducible, so if it's F join all these HI, then it's actually a single HI called HJ suffices. Okay, so that's that part of the proof, and then for the other part of the proof, remember there was another definition that one is the least degree such the cone above it is dense. For that we use of this lemma here, that we have the equivalence for partial multivariate function that ID is Weihrauch-reducible to not Weihrauch-reducible to F if and only if there is a minimal cover, a pair minimal cover GH above F. Of course, that clearly defines whether or not F is less or equal ID. So therefore, in particular, the Weihrauch degrees above 1 are dense, and 1 is the least degree, such that the Weihrauch degrees above it are dense. Okay, so I think I've told you everything I want to say. The rest is in the paper if you want to see the details, and I thank you for now.
Yes, one, so is there anything known about the complexity of the theory of Weihrauch degrees above 1?
I am not sure. So there is in another paper, a similar group, Valenti and Joe and I, and but now with Alberto, showed that there is a notion of a jump operator, which is degree theoretic, unlike the usual jump in the Weihrauch degrees, and that is actually an embedding of the Weihrauch degrees into the Weihrauch degrees above 1.
Aha.
So it's not just order preserved, but actually it is strict order preserving. But the image is, I mean, but the range is definitely not on 2. So I'm not sure. You might be able to pull somewhere, because I mean now we said once you have the jump, right? I mean you can look at the jump of 1. So it turns out that 0 has jump 1, and then 1 has another jump. And then you could look at the next interval and see what's going on there, but I'm not exactly sure whether that would answer your question. Yeah, so I don't know. The answer is I don't know. I mean, there's some ideas that I couldn't think of, but I don't know the answer.
Thanks. Other questions? If not, let's thank Steffen again.